art of classification. If you've ever trained a model and seen a high accuracy score, you might have felt a rush of excitement. You might think, my job is done, this model is perfect. But often that number is a lie, or at least a very dangerous illusion. In this video, we're going to move beyond simple accuracy. We're going to dissect how we actually evaluate classification models using the famous MNIST dataset as our laboratory. We'll look at why 96% accuracy can sometimes be a failure, how to interrogate your model using a confusion matrix, and how to master the delicate tug of war between precision and recall. Whether you are building spam filters, medical diagnostic tools, or image recognizers, understanding these metrics is what separates a novice data enthusiast from a true machine learning practitioner. Let's get started. Before we jump into the code, let's ground ourselves in definitions. In supervised learning, we primarily deal with two types of problems: regression and classification. In a previous video, we looked at regression, which is all about predicting a specific numerical value, like estimating the price of a house based on its square footage. Classification is fundamentally different. Here, our goal isn't to find a number, but to teach the machine to see categories. We want the model to look at an input and predict a discrete class. This is the technology behind your email provider deciding if a message is a spam or not a spam. It's how your phone sorts your photo into cats or dogs. And it is the critical logic behind medical AI distinguishing between a benign and a malignant tumor. In this session, we are focusing strictly on classification, starting with the simplest form, distinguishing between two distinct buckets. To learn these concepts, you need a dataset. We will be using the Hello World of Machine Learning, the MNIST dataset. If you study machine learning, you will encounter this data sooner or later. It is a massive collection of 70,000 small images of digits handwritten by high school students and Census Bureau employees. Each image is a tiny grayscale square, 28 pixel high by 28 pixel wide. When we flatten this grid out, we get a vector of 784 features. Each feature represents the intensity of a single pixel, ranging from 0, which is white, to 255, which is a pitch black. Our goal is straightforward but challenging. We need to train a computer to look at these 784 pixel intensity values and correctly predict which digit from 0 to 9 the human wrote down. It sounds simple to us humans, but for a computer, it's a complex pattern recognition task. Trying to distinguish between 10 different digits all at once can be overwhelming for a first attempt. So, to understand performance metrics, we are going to simplify the problem a bit. We will turn this into a binary classification task. We are going to build a 5 detector. This model will have two possible answers. Either the image is a 5 or it is not a 5. To do this, we modify our target vectors. As you can see in the code snippet, we create a Boolean array where the label is true if the digit is a 5 and false for every other number. We'll start by training a Stochastic Gradient Descent or SGD classifier. This is a linear model that handles large datasets very efficiently. We feed it our training data, and within moments, it learns to distinguish the character 5 from the rest of the pack. But how well did it actually learn? We train the model and then we evaluate using k-fold cross-validation. If you recall, this technique splits our training data into 3 folds: training on 2 and testing on the third, rotating through to ensure robustness. The results come back and they look absolutely spectacular. Look at those numbers: 95%, 96%, 96% accuracy across the 3 folds. In almost any other context, like a history exam or a batting average, getting 96% is very close to perfection. You might be tempted to pop out the champagne and deploy this model and call it a day. It seems like our SGD classifier is a genius that rarely makes a mistake. But I'm here to tell you to pause. In machine learning, whenever a result looks this good on the first try, you should be suspicious. Is our model actually perfect, or is there something else going on here? This brings us to one of the most important lessons in classification, the deception of accuracy. That big, bold 96% is a dangerous illusion. Accuracy is simply the ratio of correct prediction to the total number of predictions. It sounds like the only metric you need, but it has a fatal flaw. Accuracy creates a blind spot when you're dealing with what we call as a skewed dataset. A skewed dataset occurs when some classes are much more frequent than others. In our case, we are trying to detect the number 5. But think about the distribution of digit. The number 5 only makes about 10% of the dataset. The other 90% are non-5s. This imbalance fundamentally breaks accuracy as a reliable measure to skill. To prove this, we're going to perform a little experiment with a completely unintelligent model. Let's prove why accuracy failed us. We're going to build what we call as a dummy classifier. This model has zero intelligence. It doesn't look at the pixels, it doesn't learn patterns, it has one simple rule. No matter what image you show it, it simply guesses not a 5. If you show this dumb classifier a generic image from the MNIST dataset, it will be correct 90% of the time, simply because 90% of the images aren't 5s. If we evaluate this dumb classifier, it scores 90% accuracy. Our complex SGD classifier scored 96%. That means all that math, training, and gradient descent only bought us what? 6% improvement over a model that does absolutely nothing? This reveals the critical insight. Accuracy is a misleading metric for a skewed datasets. We need a tool that doesn't just tell us how many times we were right, but how we were right and how we were wrong. To get the real story, we need to open up the hood and look at the confusion matrix. This is your ground truth. Instead of summarizing performance into a single number, the matrix breaks down every prediction into 4 specific categories based on the actual class versus the predicted class. Here's how you read it. The row represents the actual classes, what the image really is. The column represents what the model predicted. If the image was not a 5 and predicted not a 5, that is a true negative. If we mistakenly shouted 5 when it wasn't, that is a false positive. If the image was a real 5 but we missed it, that is a false negative. And finally, if it was a 5 and we got it, that's a true positive. By filling in these 4 boxes, we can see exactly where the model is confident and where it is confused. Let's populate this matrix with the actual data from our SGD5 detector. We use cross-validation predictions to ensure we are testing on data the model didn't explicitly memorize. Look at the top left, 53892. These are the non-5s correctly identified. This massive number is why our accuracy looked so high. The model is great at ignoring non-5s. But look at the errors. Top right, 687 false positives. These are ghost images the model thought were 5s, but they weren't. Bottom left, 1891, false negatives. This is the painful part. There are nearly 2000 real number fives that our model completely ignored. Accuracy hide these 1891 mistakes behind the mountain of 53,000 correct negatives. But depending on your problem, those 1891 missed detections could be catastrophic. We need metrics that isolate these specific types of errors. From the confusion matrix, we derive two metrics that are far more useful than accuracy: precision and recall. First, precision. This asks, when the model claims an image is a 5, how often is it right? We calculate this by taking true positives and dividing by all positive predictions. Our score is 83.7%. This means when a model cries wolf, it's right about 80% of the time. Second, recall. This asks, of all the actual 5s in existence, what fraction did we actually find? Here, we divide true positives by all actual positives. The score is 65.1%. This is the shocking reality check. A 96% accurate model actually fails to detect more than one third of all the 5s in the dataset. If this were a cancer detector, detecting only 65% of the positive cases would be unacceptable. These two numbers tell the true story. You might ask, can't we just maximize both? Uh, Unfortunately, in most machine learning algorithms, these two metrics are at war. This is the precision recall trade off. Increasing one usually hurts the other. You have to decide which is more important for your business case. Imagine you're filtering videos for children, safe versus unsafe. You need high precision. You simply cannot allow a bad video to slip through. You don't mind blocking some safe cartoons. Low recall, as long as everything that gets through is definitely safe. On the converse side, imagine detecting shoplifters. You want the high recall. You want to catch every thief. If the security guard checks a few innocent people with a low precision, it's annoying, but it's better than letting the thieves walk away. You must choose the right balance based on the cost of your errors. How do we actually adjust this balance? We do it by tweaking the decision threshold. Under the hood, the classifier doesn't just output 5 or not 5. It calculates a numerical score for every image. If the score is higher than a certain threshold, it predicts positive. If it is lower, it predicts negative. Imagine the blue line in this visual is all our images arranged by a score. The 5s generally have a higher score to the right, and non-5s have a lower scores. If we raise the threshold, slide this orange bar to the right, we become very strict. We eliminate false positives, so precision goes up. But we also leave some real 5s behind, so recall goes down. If we lower the threshold, slide left, we become lenient. We catch all the 5s, which is equivalent to high recall, but we also accidentally let in a bunch of non-5s, tanking our precision. This threshold is your control dial. To find the perfect threshold, we don't have to guess. We plot the precision recall or PR curve. This graph visualizes precision against recall for every possible threshold setting. The ideal spot would be at the top right corner, 100% precision and 100% recall, but reality is a curve. Look at the blue line for our SGD classifier. You can see it hold steady for a while, but once we try to get recall above 80%, precision falls off a cliff. This curve allows you to make an informed business decision. If your boss says, we need 90% precision, you can trace that line on the y-axis. Find where it hit the blue curve and see exactly what recall you will have to sacrifice to get it. In this case, to get a 90% precision, we'll have to accept a recall somewhere around 50 or 60%. There's another famous curve you'll see in the literature, the ROC curve, or Receiver Operating Characteristics curve. Instead of precision versus recall, this plots the true positive rate, which is just recall, against the false positive rate. The false positive rate is the ratio of negative instances that are correctly classified as positive. Ideally, we want the blue line to shoot straight up to the top left corner, maximizing the true positives while keeping the false positive at zero. The dotted line represents a purely random guess. The area under curve, or the AOC as we call it, gives us a single score to grade the model. A perfect model has an AOC of 1, a random guess is 0.5. Here's a pro tip for you. Use the PR curve, which was in the previous slide, when your positive class is rare, like our 5s. Use the ROC curve when your classes are balanced. Since 5s are rare, the PR curve was actually the more honest visual R for our model struggle. Now that we have some sophisticated tools, confusion matrices, PR curves, ROC, AOC, we can use them to compare different models properly. We are going to orchestrate a showdown. Our current champion is the SGD classifier. It's fast and simple, but as we saw, it struggled to maintain high recall without losing precision. Let's bring in a challenger, the Random Forest Classifier. Random forests generally capture more complex, nonlinear patterns in the data by averaging out the prediction of many decision trees. Let's see if this complexity pays off on the MNIST dataset. To compare them, we train a random forest on the same 5 detector task. There is a slight technical difference in how we get the scores. The HGD classifier gave us a decision function score. The random forest works a bit differently. It uses a method called predictPro. This returns the probability, a percentage chance, that a given image belongs to the positive class. For example, it might say, I'm 89% sure this image is a 5. We can use this probability just like a score. We treat higher probability as higher scores and map out the same curves. By feeding these probabilities into our evaluation function, we can generate a PR curve specifically for the random forest. The results are in, and the visual evidence is undeniable. Look at the comparison graph. The dotted line is our old SGD classifier. The solid blue line is our random forest. The random forest curve is pushed incredibly close to the top right corner. This is exactly what we want to see. At the same level of recall where HGD struggled, random forest maintains near perfect precision. If we look at the metrics table, random forest achieves 99% precision while still maintaining 87% recall. Its F1 score jumps from 0.73 to 0.93, and the ROC AUC is practically perfect at 0.998. By using these advanced metrics, we have empirically proven that the random forest is the superior model for this specific task, far beyond what a simple accuracy score could have told us. We have mastered the binary 5 detector. Yippee! But the real world is rarely just a yes or a no. The MNIST dataset actually contains 10 distinct digits, 0, 1, 2, 3, all the way to 9. We need to move from binary classification to multi-class classification. Scaling up presents new challenges. Some algorithms like random forest or logistic regression can handle multiple classes natively. You just feed them the data and they figure it out. But others, like the support vector machine or the HGD classifier, are strictly binary. They only understand how to draw a line between group A and group B. So, how do we use a binary tool to solve a 10 class problem? Here, to adapt binary classifiers for multi-class problems, we use clever strategies. The two most common are one versus the rest, OVR, or one versus one, OVO. In one versus the rest, we train 10 separate systems, a zero detector, a one detector, and so on. To classify a new image, we run it through all 10. Whichever vector screams the loudest, gives the highest score, wins. This is the default for most algorithms. In one versus one, we train a binary classifier for every specific pair of digits. One to distinguish zeros from ones, another one for zeros versus twos. For 10 classes, this requires 5 distinct classifiers. When predicting, we run the image through all 45 duels. The class that wins the most duels is the final prediction. This sounds tedious, but it is actually preferred for algorithms like SVMs that struggle with large dataset sizes, because each classifier only trains on a tiny slice of data. When we train a model on all 10 digits, the confusion matrix becomes even more vital, but also more complex. It's now a 10 by 10 grid. If we look at the raw numbers, it's hard to find patterns. But if we plot it as a heat map and normalize the values by the row, insights jump out at us. Look at the diagram on the right. The diagonal is bright, which is good. It means most digits are classified correctly. But look closely at the row for the number 5. It's dimmer than the others. The model only correctly identifies 5s about 82% of the time. Where are the mistakes happening? Look at column 8. There are the bright patches in the 8 column for digit like 5. This tells us specifically that our model is confusing 5s for 8s. This is actionable intel. We now know we don't need to fix the whole model. We specifically need to help it to distinguish the loop of an 8 from the shape of a 5. Let's add another layer of complexity. Sometimes one answer isn't enough. Imagine a face recognition system looking at a photo of Alice and Charlie. It shouldn't just say Alice or Charlie. It needs an output tag for both. It's a multi-label classification. In MNIST, we can simulate this. Let's create a system that predicts two things simultaneously. Is the number large? 7, 8, or 9? Is the number odd? If we feed in the number 9, the model should output the vector true, true. We can use algorithms like k-nearest neighbors for this. We simply train it on a matrix of multiple labels. When we evaluate it, we can calculate the F1 score for each label individually and average them out to get a sense of how well the model handled this multifaceted reality. Finally, we arrive at the most complex frontier, multi-output classification. This generalizes the concept even further. Here, we don't just have multiple labels. Each label can be a multi-class variable itself. The best example is image denoising. We take a clean image and add noise to it. The input is a messy static filled image on the left. The output we want is the clean image on the right. Think about what the model has to do. It has to predict a value for every single one of 784 pixels. And each pixel can be any intensity from 0 to 255. Technically, this blurs the line between classification and regression, but we treat it as a multi-output classification task. We train the classifier to predict the correct class for every pixel simultaneously. The result is a system that can magically wipe away noise and restore data. We have covered a tremendous amount of ground today. Let's review the core tools you should now have in your investigator's toolkit. First, never blindly trust accuracy. If your data set is skewed, accuracy is lying to you. Second, the confusion matrix is our best friend. It's the only way to see the true nature of your errors. Third, master the precision recall trade-off. There's no best model, only the model that best fit the cost of your specific business problem. Use PR curves to find that sweet spot. And finally, analyze your errors. A model failure isn't a dead end, it is a clue. Whether it is a confusing 5s or 8s or failing on rotated images, the error tells you exactly how to build a better system. Thanks for watching. Go out there, ignore 96% accuracy hype, and start building models that actually work. Subscribe for more. Thanks.